So in this class we are going to discuss some basics of matrix representations. So first we will look how the vectors are represented in Euclidean space, or how we can represent these vectors in matrix form. So let's consider the example of a position vector in two-dimensional space. So while dealing with vectors, it is very useful to express any vector in a linear combination of a pair of basis vectors. So we need a coordinate system such as a pair of x and y axis, and then describe the vector in terms of its components with respect to this axis. So let's consider our familiar unit vectors I and j. Then in two dimension, any vector can be written as vector r is equal to xi plus yj. So it gives the components of this vector r along the unit vector I direction and along the unit vector j direction. So any position vector can be written in this way. So that is, these unit vectors constitute a pair of orthonormal basis vectors, and x and y are the components of R with respect to these basis vectors. Then after representing it in this way, we can perform some operations like we can add, or we can do scalar multiplication working solely with these components. So for example, if we have two vectors r1 and r2, let's say r1 equal to x1i plus y1j, and r2 equal to x2i plus y2j, then if you want to add these two vectors r1 and r2, this is simply x1 plus x2i plus y1 plus y2j. So that means you can perform various kinds of operations by simply adding the components of the vectors. Now it is important to note that while a vector is unique geometrical object, there is no unique choice of basis vectors. Hence the components of the vector will change depending on the choice of basis vectors. Thus we could equally will have chosen the basis vectors, another set of basis vectors I prime and j prime, like this one. Let me draw. So I have drawn two set of coordinates. One is with respect to these I and j, which is shown by this yellow color, and another set of coordinates which is a primed coordinate system, which is shown in that this pink color, which is I prime and j prime. Now we have a unique vector r, and I told you that while r is unique, the components are not unique. It depends the way you define or the way you take the coordinate system. For example, if you are considering this yellow coordinate system, then its components are given by x and y. So it can be written something like this: x I plus yj form. But if you had chosen this pink coordinate system, then you can write the same vector r as x prime I prime plus y prime j prime, where these x prime and y prime represents the components of the vector along this x primed coordinate system along the x I prime direction and j prime direction. Now if you note, you can say that this x prime is not same as x and y prime is not same as y. So that means even though these two quantities in the unprimed coordinate system you had written is something like this: x I plus yj. So even though these two things are same, see, these components are not identical, they are not same, because so it depends the system or the coordinate system we choose. Okay, so once a choice of basis vectors have been made, it is very convenient to work solely with the coordinates. So there is useful a notation by which this can be done. So in this notation, a vector r can be written like this. Vector r is represented as x, y, the components of the vector. Now this symbol means this equal to with a dot is represented by. It means it is represented by, not equal to. So r can be represented once you fix your coordinate system. You may choose like I have fixed my coordinate system as this one, then its components can be represented by this form. Means this vector can be represented by its components x and y. So this is known as a column vector. It's a column vector, and this column vector is a representation of the vector r with respect to the basis vectors I and j, right? Now we use this symbol represented by to emphasize the fact that while the vector r is a unique geometrical object, its components are not. So they depend on the choice of the basis vectors. See, we could have equally chosen the basis vectors I prime and j prime, right? So in that case, you could have written it as vector r represented by x prime, y prime, right? So this right hand side is not unique. It depends the coordinate system we choose. So two different column vectors basically. This is one column vector and this is another column vector, and two different column vectors representing the same vector r. So equivalently, if we had two column vectors with exactly same numbers in two position, we could not conclude that they represent the same vectors unless we were told that the basis vectors were the same in each case. Okay, so once a choice of basis vectors have been settled on and consistently used, we can proceed with the vector calculations using a new notation using this column vector form. Now the scalar product of the vectors r1 and r2 which we considered before is given by r1 dot r2. So this is r1 r2 cos theta, right? So this can also be represented in the form of components of r1 and r2 in ij basis or equivalently I prime j prime basis. So r1 dot r2 is equal to basically x1 x2 plus y1 y2, right? Because this is r1 we had written of the form of x1i plus y1j, and r2 was written in terms of the components x2i plus y2j. Now when you take the dot product, this will give you x1 x2 plus y1 y2. Now using the rules of matrix multiplication, we can write it as something like this: x1 y1 then x2 y2, right? So this is a row vector and one is a column vector. Now this will give you the same thing, right? If you take the product of these two these two vectors, this will give you these components x1 x2 plus y1 y2, and you know how to multiply the elements of the matrix. So here the components of the first vector is represented by the row vector, and if the components of r1 and r2 were complex, then we would write the inner product as this. The inner product is usually written as, if you have r1 r2, the inner product of r1 and r2, the comma, this is for complex vectors is written in this form: r1 star dot r2. So this will be basically x1 star. You know, if you take the complex conjugate of the first entry here, what you get is x1 star x2 plus y1 star y2. Then in matrix form you can write it as x1 star y1 star, then x2 y2. So once the vectors are represented properly by row and column vectors, the rules of matrix algebra can be used. So there is some deeper significance in this form of notation. Corresponding to any vector r represented by a column vector, there corresponds another vector r star known as the dual represented by a row vector. So for any vector r, there is a dual which is represented by r star. Then when we represent this by a column vector, this is represented by a row vector. The original vector is the physical vector, while its dual is an abstract mathematical companion. Now the original vector and its dual belongs to two different bases. This one and this one belongs to two different spaces. Now let's see how to represent the state vectors and operators in a similar fashion. So we introduce a complete set of orthonormal basis states phi n, where this n equal to 1, 2, 3, etc. Now this span the state space of a quantum system. So these basis vectors span the state space of a quantum system, and then we work with the components of the ket, bra and operators in this space. We cannot interpret these basis vectors as representing the physical directions in real space. They are abstract vectors in a multidimensional complex vector space. But much of what is done in connection with the vectors in ordinary Euclidean space can be carried over to this more abstract situation. So what we have considered is a discrete, complete and orthonormal basis vectors given by this phi n. Now it's discrete, but it can have infinite number of unit vectors. This can go to an infinite number of unit vectors. Then we say that this phi 1, phi 2, etc. is countably infinite when we have an infinite number of discrete basis vectors. I said what are the properties of these basis vectors? It must be complete and orthonormal. So this is orthonormal, and this must be complete. So what does it mean? The orthonormality condition of the base vectors is represented by the statement phi n phi m, the inner product, is equal to delta m, and the Kronecker delta function. So this is what you mean by orthonormal, right? Now the completeness or the closure property is given by sigma n equal to 1 to infinity, the basis vector is phi n. So phi n must be I, the unit operator or the identity vector. The unit operator or the identity vector. So this is the completeness. This is what basically mean by the completeness condition. You sum the projection operators in that space, sum the entire projection operators, and that will give you the unit operator. So this is the projection operator that we have discussed in our previous class. So now let's see how to represent the Katz and Brass in matrix form. So for this we consider the representation of the state vectors psi of any quantum mechanical system within the basis phi n, which we have defined just now, where this n is equal to 1, 2, 3, etc. to infinity. Okay. Now we use the completeness property of this basis to expand the state vector. So any state vector can be expanded like this. You multiply it with the unit operator, and this will, the unit operator acting on the this ket vector leaves the ket unchanged. So this is the same thing. Now we use the completeness property, because if you take the sum of the entire basis vectors or the entire projection operators, and then you will get 1. So this can be sigma n equal to 1 to infinity phi n. So this is basically the unit operator that we considered, because when you sum it you will get 1. Then you multiply it with the state vector psi, right? So this can be written in a more compact form like this: sigma n equal to 1 to infinity an phi n. Okay. Now the coefficient an, if you compare this, you can see that it basically represents this inner product phi n psi. Now it represents the projection of this psi vector onto this phi n, right? So an is the component of the psi along the phi n direction, and these coefficients are in general complex. They are in general complex quantities. So this is quite similar the way we represent a normal vector. For example, if we consider a vector A in a two-dimensional space x and y, then if you have a unit vector I along this, to get the ax component, what you have to do is you will be taking the dot product of I with vector A, and this will give you the x component. So similar fashion, you can see that this one represents basically the projection of this psi vector onto this phi n axis. So those are the coefficients that appear here in these expressions. So within the basis phi n, the ket psi can be represented by a set of coefficients a1, a2, a3, etc. along phi 1, phi 2, phi 3, etc. respectively. So a1 is the projection of psi along psi 1 direction, and a2 is the projection of psi along phi 2 direction, a3 is the projection of psi along phi 3 directions, like that way. So psi can be represented by a column vector which has countably infinite number of components. So in vector form you can write it as the state vector psi or the ket vector psi can be written by the coefficients. And what all are the coefficients you can have? You have the coefficients of psi along phi 1, psi along phi 2, etc. Phi n, psi, etc. It can have an infinite number of coefficients. So this is basically the coefficients a1, a2, etc. like an, etc. So what I have shown is a column vector can be represented. A column vector can be represented by a state vector can be represented by a column vector. Okay, so in a similar fashion, a bra vector can be represented by row vectors. For example, if we consider the bra psi, this can be multiplied by the unit operator. So this is same as summation over n equal to 1 to infinity. You have bra psi, then this phi n. So this is basically summation over 1 to infinity a n star, then you have phi n, right? Where a n star, the coefficient a n star is given by this quantity, that is the inner product between psi and phi n, right? So this is basically the inner product or the projection of the psi along the phi n direction, and if it takes the complex conjugate, so that is what a n star, okay, the complex conjugate. So how do you represent a row vector? So this can be represented, or a bra vector can be represented in a row vector form by its components a1 star, a2 star, a3 star, etc. So what are a1 star? a1 star is given by psi phi 1, and the next component is given by psi phi 2, etc. psi phi n, etc. So this is basically a1 star, a2 star, a3 star, etc. an star. So it's a row vector of complex numbers, or means complex conjugate of these coefficients. So if you follow this representation, then a bracket can be, so let's consider a bracket psi and chi. So this kind of combination are complex numbers equal to the matrix product of a column matrix corresponding to this ket vector and row matrix corresponding to this bra vector. So how do you write it in matrix form? This can be written as a row vector corresponding to psi. So this is given by a1 star, a2 star, etc. up to an star. then multiplied by, let's put another coefficients for this chi vector. So this is represented by a column vector b1, b2, etc., bn, etc., right? So this can be written as summation over n equal to 1 to infinity an star bn. Okay. So this is the matrix representation of a scalar product between two vectors chi and psi. And now let's see how to represent the operators in matrix form. So let's consider a discrete, complete and orthonormal set of bases, the same basis what we considered just before. So it's a basis set phi n where n can be 1, 2, 3, etc. up to infinity. Now for simplicity, let's assume that this n is finite. That means let's say it is finite up to some maximum number. Yeah. Let's consider an operator a which acting on a ket vector psi. So this should transform it into another ket vector. So that is basically what operators do. An operator when acts on some vector transforms it into another vector. So let me write it in this way. Chi is equal to a acting on psi. Okay, so now we expand both this chi vector and the psi ket, chi ket and psi ket in phi n basis. So how do we do that? We use the completeness property of these bases. So you can write it as sigma n equal to 1 to n phi n, the sum of basis vectors, projection operators of basis vectors phi n chi, because this is basically the identity operator or the unit operator. So this is can be written as, on right hand side again you can write it n equal to 1 to capital N operator a, then phi n phi n, then you have this psi vector. Okay, so this on left hand side can be written as sigma n equal to 1 to capital N an phi n, where n is the coefficients, and this is equal to sigma n equal to 1 to n the vector a, then you have phi n, then another set of coefficients bn. Okay, so what are these coefficients? bn is given by this inner product, and an is given by this inner product. an is given by this inner product. Okay, now let's multiply both sides with a bra vector phi m. So both sides of these equations can be multiplied by a bra vector phi m, then this will give us sigma n equal to 1 to capital N, you have the coefficients an, then bra phi m ket phi n, this is equal to sigma n equal to 1 to n. On right hand side what we have is you have to multiply it with the bra phi m then you have this vector, then you have phi n, then the coefficients bn. Okay, and this order is very important because the ket is multiplying on the left side of this operator. Yeah, so on left hand side what you have is sigma n equal to 1 to capital N an. Now these are basis vectors, so the orthogonality condition or the orthonormality condition will tell you that this scalar product will be delta mn, the Kronecker delta function, and this is equal to, on right hand side you have n equal to 1 to capital N, and then we put these quantities, this matrix product by something called the matrix elements A, M, N, then you have Bn, where A, M, N is given by all these quantities phi m, A, phi n. Okay. So on left hand side what you have is because of this Kronecker delta function, the only surviving term out of these many summations, the only surviving term is am, that is when n equal to m. So what you have on left side is am, and on right side is this is n equal to 1 to capital N am n bn. Okay, now let's assume that this maximum dimension, for simplicity let's assume that this is 3. Then this equation tells us that if you write it explicitly, you can write it as a1 equal to a11 b1 plus a12 b2 plus a13 b3, because both your m and n will be having values 1, 2 and 3, right? So similarly you can write a2 is equal to a21 b1 plus a22 b2 plus a23 b3, and a3 can be written as a31 b1 plus a32 b2 plus a33 b3. So this is the situation when you take this n is equal to 3, right? So this can be written in a more convenient or compact form like this, in a matrix form. You can write it as a1 a2 a3. So this is a column matrix or column vector, and then you can write it as product of two quantities a11 a12 a13 a21 a22 a23 a31 a32 a33 multiplied by another column vector b1 b2 b3. So this is same as above expression, right? So it basically tells you that the column vector, so what are these a's? These are the coefficients of the column vector chi. So the column vector chi can be represented by the vector chi can be represented by a column vector or a column matrix, and this is a square matrix, and this square matrix represents the operator which we considered, and this is another column vector which represents the chi vector that we considered. So if you generalize these to infinity, that means if you generalize this phi n basis like this n goes to infinity, then you can see that an operator A can be represented by a square matrix. It can be represented by a square matrix. So an operator will be always represented by a square matrix, and that has countably infinite number of columns and countably infinite number of rows. Okay, so in general you can write any operator A which can be represented like this, can be represented by a square matrix A11, A12, etc. A21, A22, etc. So in that fashion it can have uncountably infinite number of rows and columns. So what we have seen in all these representations is that a ket vector can be represented by, or a ket can be represented by a column vector, and a bra can be represented by a row vector, and any operator can be represented by a square matrix. So these are the matrix forms of operators: ket, bra, and operators in quantum mechanics.